In science, generally, we use what's called the SI unit system. There's all sorts of units for all sorts of these different kinds of measurements. But the SI system is the one that we settle on. Does anyone know what SI stands for? Sorry? The S is scientific, and I is international. They're backwards because it's French. I butcher the pronunciation every time, but we'll try it. It's like the Scientifique d'International, the units. What are they? What is our scientific standard unit for length? The meter, yes. Spelled E-R-S, sometimes it's spelled R-E-S. Here, real exciting. The symbol for the meter is M. Again, this is not rocket science, but there it is. Mass. Mass is not the gram. You would think it would be the gram because length is meter. It's related to the gram. It's the kilogram. It is the only base unit that has a prefix to it already, the kilo part. Time, measured in seconds. Okay, right. In kilogram, we'll go to kgs. Seconds is obviously S. Speed is meters per second. It makes sense if distances are meters and times in seconds, then speed would be meters per second. We'll give you a handy-dandy conversion to and from kilometers per hour in a second. Force. We spent a lot of time in physics talking about forces. Does anyone know how we measured those forces, or what units we used to measure those? Sorry? The Newton. Named after exactly who you're thinking, the Newton. So many of these units that I'm going to introduce you to over the course of the semester are named after famous dead people. The unit for force is obviously named after Sir Isaac Newton, a wild and wacky, literally wacky dude, but very, very intelligent. The Newton is capital N, because lowercase n is something else. Energy. We spent some time measuring energy. Does anyone know? The joule. Named after a French physicist of the same last name. And a capital J there. There's other ones that we are going to use over the course of the semester, but this gives us a decent foundation for what we're going to do now, which is you could do some unit conversions. It's only useful to talk about these units if we can move back and forth between different versions of these units. And so what we do to talk about the sizes of these things is we add prefixes. Obviously, kilogram has that kilo there. What does kilo mean? Why do we throw kilo in front of gram? Yeah, because kilo is 1,000 grams. The symbol for kilo is K, and it is means you've got a factor of 1,000. We're also going to use that in exponent notation, 10 to the 3. This, that. There we go. Because we're going to be playing with scientific notation here in a little bit. If there is no prefix, obviously there is no symbol, that is just the factor of 1 of something. This little chart here is not all of the prefixes, but it's some of the most common. Let's go up. Mega. What is mega of something? A megagram. A mega would be, sorry, Dimini? It would be a million of something, yes. The prefixes tend to go up by 3s in the exponent. So mega is capital M. Lowercase m is something different. Centi. Centi is not one that we use often, but it gets used periodically. When we're dealing with centimeters, we just typically use decimals of meters. But centi, the symbol is lowercase c, which you should be familiar with. And this is a factor of what? How are centimeters and meters related? Consonant. 100, or 1/100th. Yeah. Because there's 100 centimeters in a meter. A centimeter is 1/100th of a meter, or 10 to the negative 2 of something. Milli is more commonly used than centi, believe it or not. A milli means what? How many millimeters are there in a meter? Constant. Yeah, there's 1,000 of them. So milli means 1/1000th, or 10 to the negative 3 of something. And it is a lowercase m. And now we're going to go back into this pattern of going up or going down or up or down by exponents of 3. Micro is the next one. Micro is 10 to the negative 6, which makes it 1/1,000,000th of something. If you have a micrometer, there are 1,000,000 of those in a meter, which is weird to think about because this is a meter. And to divide the stick up into 1,000,000 little pieces would be pretty wild. But a micrometer is 1/1,000,000th of this. We'll leave it there because I'm going to refer to it. Does anyone know the symbol for micro? Have you seen it anywhere? Yep.
Isn't that wild U?
It's actually a wild U, but yes.
Oh, yeah.
That guy? Yeah. We are going to use this symbol for other things as well. This is the Greek letter mu, mu, lowercase mu. In the context of units, it stands for micro. In the context of in the context of forces, it's going to be related to something involving friction. We'll get there. So just be prepared for that to take on an alternative meaning. If you have taken chemistry already, you should be familiar with exactly what we're about to do. You spend almost all of Chemistry 11 is just flipping back and forth between different kinds of units. Or even you take density and you want moles of something. So there's a bunch of conversions you got to do along the way. That method is called the factor label method, and it's what we're going to use here to do our unit, or to give our unit conversions a framework. So this thing is called the factor label method for unit conversions. And once you get yourself comfortable with this particular method, it makes this whole exercise trivial. But if, like so many students, you're like, nah, I got a better way to do it, you will continue to struggle. So if I wanted to convert, for example, 165 millimeters to meters, intuitively, should that 165 get bigger or smaller? It should get smaller, because meters are bigger than millimeters. So if you have 165 of something small and you want to go to something bigger, it should be a smaller version of that larger thing. Hopefully that made sense. So at least we've got an idea of what we're trying to get to. Here's how we go about it. If I have 165 millimeters, what we're going to start to do is we're going to start to multiply by fractions. Sorry, for those of you who hate fractions. We're still multiplying by fractions to help us cancel out our units. Because units cancel just like variables do in math, just like constants do in math. Units behave the exact same way. So if I have 165 millimeters and I want to turn this thing into meters, there is one nice straight conversion we can go to. We're going to multiply this thing by a fraction that cancels out the millimeters and replaces it with meters. If I have millimeters in the numerator to start and I want to cancel it out, where should the millimeters show up in this fraction? In the bottom, in the denominator. And I want to replace them with units. Meters. So that's what's going to go up top. And we have a nice conversion between meters and millimeters. How you choose to fill in what remains here will depend on how you want to use these numbers. There's like 3 or 4 different ways to comfortably write this out. I'll show you both of them. We'll start with the scientific notation-y piece, and if you like that, then great. If not, I'll show you an alternative method down here. So, millimeters, 1 millimeter. This first method is we're going to swap out the prefix on milli with its appropriate power of 10. So the prefix milli on the millimeters is 10 to the negative 3 of something. So 1 millimeter is 10 to the negative 3 meters. and then we're just going to ram that through our calculator if you need to. This is not like most math classes that I teach where I require my students do so much in their head. You can. This is not hard to do in your head. It's powers of 10. Yes, sir. It's hard. No, I got it right. Sorry, Karen. Constant.
Oh yeah, isn't it 0.165?
Yeah, it's going to be 0.165. Powers of 10 are nice and easy to move with decimals. That's why we use the scientific international system. The alternative is the imperial system, and it's gross. 2 countries use it. Tiny country in Africa, and I forget the name of the other one. It's the States, for those of you who don't know. I was making a joke, and only a couple of you got it, so I appreciate the few of you who got it. Yes, 10 to the negative 3 means I take the decimal at the beginning of the number and I move it this way 3 times. So it's going to be 0.165, because I've moved the decimal, the number of exponents that we've got here. And now I've got a smaller number. My millimeters have canceled, and I'm left with meters. If you're comfortable dealing with powers of 10 and scientific notation, this is trivial for you. If, for whatever reason, you're like, nah, I would really like to avoid using exponents at all possible, I'll give you an alternative method here for number 2. We're going to convert 380 centigrams into milligrams. Now, there is no nice conversion straight from centigrams to milligrams, because centi and milli both refer to different prefixes on the table here. So to go from centi to milli, we're going to have to go through what? Yeah, constant.
Isn't it just 10 the difference?
It is, but to write it out nicely, yes, you're going to shortcut this, but I'm trying to enforce a method here. You're right, the difference is only 10. So I can move the decimal just once. It'll be 38. Actually, no, it'll be 3,800, going the other way. But to actually go through the method I want to go through, we're going to go through grams. Yes, constant.
So if you're going to grams, wouldn't it be like we would do the same step like before and just do 1 100 and then 1 1,000?
Basically, yes. Actually, not basically, effectively, yes. So to go from 380 centigrams into milligrams, and we're going to go through grams, you're right, centi and milli are trivially close, but I'm trying to show a method, so let's do it. The centigrams here are going to cancel, leaving me with grams. So now in the next fraction, what I'm going to do is I'm going to replace grams in the numerator, put grams in the denominator, so those cancel, and the unit I want to end with is milligrams. So I'm showing you this way because we're going to do it the alternative way here. Instead of using powers of 10 replacing the unit, what you can do is you can use our understanding here of grams and centigrams. If I have 1 gram, how many centigrams do I have? I have 100 of them. So now instead of using the power of 10, I'm using the fractional notation. 1 gram is 100 centigrams. So then 1 gram is going to be how many milligrams? 1,000. And so as we go through this thing, what we now are going to do is we're just going to multiply across the top and divide by whatever's on the bottom. If you need to punch that into your calculator, you're welcome to do it. But as Constantine already said, this is a relatively easy one, because if I look already, 1,000 divided by 100 is 10. My centigrams cancel, my grams cancel. So I'm left with 380 times 10 milligrams, which is going to be 3,800 milligrams. It's trivial at this stage, but I want you to get comfortable with the method. And now I don't particularly care which of these you choose to use. If you're comfortable with the scientific notation, go for it. If you're not and you want to use these relationships, I'm totally fine. Go for it. But you're going to want to get comfortable converting through units, because we're going to get slightly more complicated ones. Things like this guy down here. And I'm going to zoom in on this, because there's a bit that's going to get shoved in here. A common conversion that you guys are going to go through, especially in this the second unit we're going to do on kinematics, is converting from meters per second to kilometers per hour and then back again, depending on the context of the question. Now we can think this through, I suppose. We can try to rationalize this. Should my meters per second to kilometers per hour, when I get this thing into kilometers per hour, should it be a larger or smaller number than I'm starting with, do you think? Your gut says smaller. Why does your gut say smaller?
Yeah, 24 meters per second. That's a big distance in a second, right?
You're right. You're right. It's less intuitive to rationalize that than it is to do these ones here. It's easy to say, well, 165 millimeters to meters. Millimeters are smaller than meters. The bigger unit will have the smaller number. As soon as you have values now with units in the denominator, it becomes a lot harder to rationalize which effect is going to be bigger, the really small thing in the denominator or the really big thing in the numerator, which is going to have the larger effect. And so for that, we're going to go through the same method, and we're going to convert this thing from meters per second into kilometers per hour. We're going to deal with each piece at a time. So let's do it. 24 meters per second. And we're going to write meters per second as a fraction because that's what it is. We're going to multiply this thing by, now you can choose, do you want to deal with the meters first or the seconds first? I don't particularly care. Deal with the seconds first, okay? So if we're going to replace the seconds in the denominator, we're going to put seconds up in the numerator, and now the question is, do you want to go straight from seconds to hours? Can you go straight from seconds to hours? Or is there an in-between sized unit we should go to that you are more comfortable dealing with? Ari wants to go to minutes, okay? And then, obviously, we don't want kilometers per minute, so we have minutes in the denominator, so we're going to put minutes in the next numerator, and we are going to replace them in the denominator with hours. So my seconds are going to cancel, my minutes are going to cancel. Now all I got to do here is shove in some values. How are seconds and minutes related to each other? 1 minute is 60 seconds. There is no nice way to do powers of 10 here when you're dealing with time because time sucks. Time is what we call base 60, given to us by the Babylonians thousands of years ago. And so we have to deal with multiples of 60 because minutes and hours are related how? 1 hour is 60 minutes. But if we look here, that's going to leave us with hours in the denominator, which is great. That's what we want. So now let's go through and deal with our meters. I don't want meters in the numerator, so we're going to put meters in the denominator to cancel it out. And I'm going to replace them with the kilometers. It doesn't ultimately matter now if you want to use the scientific notation or if you want to use just the relational values we have over here. How do you want to relate kilometers and meters to each other? I don't particularly care. I'll do whatever you want. Constantine. Sure, we can decide. Sure, let's do it. So then, what am I going to put here? Is going to go where?
It's going to go down.
Right. So if I'm going to use the scientific notation, 1 kilometer, and then I'm going to use the correct power of 10 to replace the prefix kilo. Kilo is 10 to the 3. So now all I've got to do here is I multiply across the top and I divide by the thing that's in the bottom. So I'm going to have 24 times 60 divided by 1,000 is going to equal, someone with a calculator, what's that value? You're going to want to have your calculators handy basically all every class. So if you haven't already, get those things out. What's that value? 86.4. And I like it if multiples of you give it to me, just so we have math by democracy. If someone can verify, that's always good. So we've got 86.4 kilometers, which means, Gavin, you're right. The number it got larger. 24 meters in a second, it's a pretty big distance to go in 1 second, is 86.4 kilometers per hour. Means it's fast, but it's too slow for the freeway. This portion right here, this is likely the last time I want you to make this direct conversion, because there is a lovely little number that pops out of this little pink box that I've just drawn. What is just that value? It's 3.6. 60 times 60 is 3,600. Divided by 1,000 is 3.6. So to go from meters per second to kilometers per hour, you can do this every time if you would like. But if you don't like, and you'd like a shortcut, the conversion between meters per second and kilometers per hour will always involve this 3.6. To go from meters per second to kilometers per hour, I'm going to draw out this cool little chart. To go from meters per second to kilometers per hour, which is what we did, effectively, what happened here is we multiplied by 3.6. So if I want to go the other way, I'm going to have to divide, yeah. This is likely the last time, the only time, you have to do this full gross, well, it's not even gross, this full conversion. If you get comfortable with this and can remember which way you go. Meters per second to kilometers per hour, you multiply. Kilometers per hour to meters per second, you divide. If for whatever reason you forget, you can always go back and use this unit conversion method just to re-verify. It's a pretty common, screwing this up at the very last stage, or at the very first stage, is a pretty common mistake. If you can rationalize it like Gavin did at the beginning and say, okay, a meter is a long way to go in a second, recognizing that these numbers should, the kilometers per hour should be bigger, you can rationalize it that way too. You've got to figure out a way to make it comfortable for you. So, there's a half hour left, and this won't take, I don't think this should take you a half an hour. I'll give you guys a choice. I can let you work on this for a bit, about 15 minutes, and then I'm going to go back and finish the lesson, or I can do all of the teaching now and let you work on your own afterwards. What do you want? All the teaching now? Does anyone disagree with what Reed said? Cool. So this page here is going to be part of your homework in a second. It's some practice on unit conversions. None of these are overly complicated. And then the last one, how many minutes are there in a year? How long in hours will it take you to count to 1 billion, counting one number every second? That's a unit conversion question. So that'll be part of your homework. Flip the page. Let's take a look at scientific notation in a little bit more detail. Scientific notation. What is the purpose of scientific notation? Sorry, didn't mean any louder. You're wearing a mask too, so you have to speak up. Condensing really small or really large numbers, yes. Used to condense very large or very small numbers. And I've given you two. These two and they're going to be the examples that we're going to use for scientific notation. For some of you, it's been a long time since you've looked at scientific notation. For some of you, hands up if you've never formally looked at scientific notation like in a math class. Okay, it happens. I don't know where it's supposed to end up. Some of my grade 9s say it's supposed to happen in middle school. So if it is supposed to happen in middle school, I'm not remotely surprised that a bunch of you didn't do it, because who knows what goes on down there. Scientific notation is used to condense very large numbers or very small numbers, because I don't want to write this out every time. I don't know if you've counted it yet. Some of you may have. How many zeros are between the decimal place and that 6? There's 32 zeros there. You've counted it?
I didn't count.
You didn't? You are correct. You are correct. If I'm not mistaken, you are absolutely correct. Let me verify that. How did you pull 32 out of your butt? I want to verify that, but yeah, I'm pretty sure you're right. You're one short. It's 33. There's 33 zeros in there. This and this are both numbers that we use in physics should you progress fairly regularly. This number here, does anyone recognize this number? Is anyone into physics and have an idea what this number might be? It is the speed of light. No, man, it's good. Keep it going. This is the speed of light. The speed of light is 299,792,458 meters per second. Takes light 8 minutes to get from the sun to the earth. Means the sun explodes. You got 8 minutes until it goes dark. It's weird to think about. What that also means is the further away we're looking at in the universe, like you look at stars, the older the light is once it's reached you, because it takes time to get here. So the stars that you see might not actually be there anymore. They may have exploded at some point in the last million or so years, or however long it takes the light to reach us, and we won't know. So the further we look away in space, the further back in time we're actually looking, which is really weird to think about and kind of awesome. So that is the speed of light. We use it all the time. We condense this thing down to a number in scientific notation. To use scientific notation, what we do is we start with where the decimal place is, and we move it, either left or right, until there is only one, let's put this in here, one leading digit. What I mean by leading digit is non-zero digit. It's got to be a number there, and we only want one of them. The number of spaces we are going to move is going to be the exponent on the appropriate power of 10. And you can either memorize what comes next, or again, you can always rationalize it here too. This number is a very large number. So the exponent on the power of 10 should be what? Constantine. Should be positive. So as you move the decimal left, converting into scientific notation, the exponent is going to be positive. If this number is very small, and I want to represent a very small number using exponents, the exponent then has to be negative. Again, you can memorize the left is positive, right is negative thing, but then it's going to be confusing once we convert from scientific notation going the other way. Or you can rationalize it and recognize what these exponents mean. Positive exponents mean the number is getting big fast. Negative exponents mean the number is getting small fast. So this number here is going to become, we're going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8 times. So it's going to become, technically in its full version, it would be 2.99792,458 times 10 to the however many times we moved the decimal. We moved it 8 times. But this hasn't actually shortened it for us at all, because all I've done now is added a decimal point, a multiplication sign, and a 10 and an 8. I'm writing down more things than I did before. So what we do with the speed of light is we also now round this thing to that leading digit. What is that thing going to be rounded to the leading digit? Constant. It's going to be 3. So we say that the speed of light is effectively 3 times 10 to the 8 meters per second. On your calculator, when you're going to use these things, sometimes this will be given to you like this, as 3, then a capital letter E, and then 8. That E means times 10 to whatever power comes next. Gavin, do you happen to know the next value? Do you recognize that number? I have no idea. That doesn't even remotely surprise me. Has anyone done any cosmology reading? Is Neil deGrasse Tyson your thing? Or Stephen Hawking your thing? Sorry? That is not the weight of an atom. It is the relationship between the energy of a photon and its frequency. Sometimes called the mass. This is called the mass energy equivalency, which I think I just spelt wrong. That should be an A, and that should be an E. Whoops. equivalence, the mass energy equivalence, which is kind of a mouthful. We name it after the guy who first started playing with this relationship. This is called the Planck constant, Planck. And it's used in quantum mechanics, special relativity, particle physics. We will never use this in this course, but it's a great example of the importance of scientific notation, because as Gavin got really close, it's not 32 zeros, it's 33 zeros from there to there, which means it's going to take me 33 to get to between the 0 and the 6. So to take that decimal one more spot is going to take me 34 jumps, which means this number is much easier to write as 6.626 is what we round this thing to. If you Google it, you'll get the full thing. But often you'll see this thing rounded to 6.626 times 10 to the negative 34. And then the units on that are kind of weird. It's actually joule seconds. We'll talk about joule seconds later. Yes, sir.
How many sig figs are we required in this like overall in this class?
I am going to teach you sig figs, but we are not going to use sig figs. I'm going to expose them to you. You need to be familiar with them, but we're not going to use them. The reason we're not going to use them is because the vast majority of what we're going to do here is theoretical in nature. When we're talking about the mass of things, I'm going to condense you to the size of a singularity, and we're going to call the mass, all of your mass, condensed down to one point. Does anyone know what point we are going to condense your mass down to? If you're an athlete, you are already familiar with this concept. If you're a football player, this is a concept you want to lower. It's your center of gravity. We're going to condense your mass down to that point. Is that reasonable? Are you actually a point mass hovering like 1.5 meters off the ground? No. Do ropes have mass? Yeah, but we're going to ignore it. Is there friction caused by air? You bet, but we're going to ignore it. And so for so much of what we do, we ignore some of these details to get really good approximations. Because yes, is there friction due to air? You bet. Do you ever experience it walking down the hall of the school? No. Because you're not the space shuttle entering orbit, or leaving orbit, entering the atmosphere that is heated to thousands of degrees just because of the air molecules rushing past it. The only point you might really start to notice it, you shove your hand out the window and all of a sudden now you feel the force of the air on your arm. But until you get to reasonable speeds, we can ignore it. Because of that and so many other details, I'll teach you sig figs, but we're not going to use them. Where sig figs become very useful is when you're working in labs, and sig figs give you a really good approximation for error, which is why you've probably used them a lot more picky in chemistry. Yeah? Chemistry is very neurotic about sig figs, and they should be, because everything in chemistry is very precise. Physics is not. There's so much that we can do making really good approximations until things get really big or really small, or actual hands-on in the lab, we can ignore sig figs. So this is scientific notation. All I want you to be able to do at this stage is to convert between them, which is, I don't think, overly difficult. I think the two examples I've given you can do enough to get you through these 7 questions. But what I'd like to do here before we go too far is review computations with scientific notation. We're not going to be adding or subtracting scientific notation by hand very often, if ever. But as Konstantin already demonstrated, being able to do them in your head relatively quickly is handy for these unit conversions. So what are we using here to do what we're about to do? Does anyone have an idea of what you've already seen before? Yeah? Yeah, so we're just using a basic understanding of exponent laws. And in fact, the only exponent laws that we're going to need here, actually there's 3 that we're going to end up using over the course of the semester, but the only 2 that you need here are the ones for the product and the quotient. When you're multiplying, you add. When you divide, you subtract. The only other one you might need is the power. When you've got a power to a power, you multiply those exponents. But when you're there, you're going to be using your calculator anyway, so I'm not going to harp on that one too much. So if I had 10 to the 3 of something and 10 to the 5 of something, and I'm multiplying those things together, this is going to give me what? 10 to the 8. Same base, I add the exponents. Now, where that really gets useful, because it's not up here, is down here. A question like h, which we're going to do right now. A question like h, we can do quick and dirty without using a calculator, because 4 times negative 5 is what? It's negative 20. And then 10 to the negative 3 and 10 to the negative 5 is going to give us 10 to the negative 8. And because I was multiplying, that's just going to continue multiplying. We multiply the values that aren't the same. They don't have the same base. And with my tens, I'm just going to deal with the exponents. Now, this thing isn't in scientific notation, so this is where scientific notation gets a little bit finicky. If I want to take this number and I want to put it into scientific notation, it's going to be -2 times 10 to the something. Which way, or yeah, the decimal, if there was one, would be right here, so I'm going to move that way. Is my exponent going to be bigger or smaller? It's going to be smaller because if we look here, I have, sorry, it's going, I should have said it wrong. It's going to get less negative, so bigger towards 0. Here we have negative times 10 to the -34. As I start to march my decimal back, I start replacing negative exponents with zeros in front. So this number is going to start to get closer to 0. It's going to get less negative. The value, the 34 is going to get smaller as I add zeros in front here. So when you're converting backwards, to go the other way, when I'm going left, the negative exponent is going to decrease. Sorry, it's going to increase. The absolute value is going to decrease. It's going to become -7. Because I'm replacing some of this negative exponent here by shuffling the decimal and getting me more places that way. So I want you to play with this. If you've never seen scientific notation, it doesn't get any harder than this. This is going to be what remains of, or well, almost complete your homework. I would like you to take a look at these unit conversions, practice those. I want you to do these, practice these, and I would like you to do this. Do not use the Scale of the Universe app. I'm going to show you it tomorrow. I want us to have fun with it as a class, so do not use this, but what I'd like you to do is, with whatever your understanding is of these values, I would like you to guess at an object that you think represents that size scale. Okay? So you're doing this half of the chart for homework. And you can get a rough estimate. So like on the meter scale, what would be an object that is a totally reasonable object to represent something that is on the scale of a meter? Without being a meter stick. Big cardboard box, even more common than that. Ari. A human being, yes. You guys are on the scale of meters. None of you, I don't think, are more than 2 meters tall. None of you are less than 2 meters tall. You're all between 3 and 6.5 feet tall. You are a great example for an object that is roughly a meter. So what I'd like you to do, again, without looking anything up, I'm not marking you on this. This is just a fun, how good are you with judging the size of these numbers? Give me objects that you think would reasonably estimate these things, and then we're going to spend about 15, 20 minutes tomorrow playing with these, playing with the app. So that's your homework. You have about 10 minutes left, which is now a good time for this. If you do not have your own paper, if you have not brought your own paper, I have these. These are 80-page coil books. If any of you would be interested in them, you may come grab one. If you're like, ooh, that's a really good idea for this other class. Too bad, so sad, go to Staples, buy your own. If you're going to use it for physics, I am happy to provide them to you. If you write big and want something larger than the 80 pagers, I've got 200 pages. And if you are a sucker for graph paper, I can give you graph paper ones as well. I have those. They were accidentally ordered, but every semester I give away 1 or 2. So if you'd like a graph paper one, I've got those. Otherwise, come now and grab a book if this interests you. If you're not going to use it, just don't take it. Use your own paper. Or Constantine, you're welcome to use your iPad. But if you'd like one of these, I have different colors. I got reds, I got blues, I got greens. Dig through here, find a color that makes you happy. I got purple. Find a color that makes you happy that you want to use. Put your name on the book. Yeah, you can have a graph paper one, you bet. Please put your name on it, so if it's left here, right here. I think they're all blue. No, that's done. If you want a graph paper one, they're on the back by the window. With math, my math binders are always great, with physics would be perfect. Red, I was trying to red. Not for me. Actually, for me, it's not here. Math is pink for me because that was the color of the math department at the university I did my master's at. So like a bright, vibrant pink is math for me. Like the pens I'm using. So there you go. You've got your homework. We'll take it up tomorrow. If you got any questions, let me know. Otherwise, there you go.
Every single notebook because it's so fast.
Ooh, bold. She took a 200.
Which letters ones?
There were 200 ones. I don't know over there. Where was that 200? Did you take a 200 and an 80?
You're the 201.
Sorry? Oh, the other one's yours. Oh, cool. I also have 200 ones, yes. If you're like itching for a 200 one, you take a 200. There you go. Yeah, so there's, I don't know if you offered it to your guys yet, there's plenty of math classes. Does everyone who wants one have one? Because we're going to be offering them to my math classes as well. That's another 9 80s that are emailed. If you manage to fill it and you want another one over the course of the semester, you're welcome that second. And I would encourage you to use that rather than cramming all of your work into the tiny space provided in this undertaking. Is it not that tiny? Make sure you have quiz first, especially if you're comfortable doing it. Oh, you got advanced one? Okay, you're fine. Then you're fine. If you took IB Chem, you're golden. Because that's all this is just conversions between moles and density and volume and all that crap. For the, one second. Ooh, okay, I forgot to give you the rest. The table up at the top does not have all of the available prefixes. This table on the bottom of your formula sheet does. I've given you all the prefixes that we use. That is a 10 to the 24 on the iota, not 29, number 24. All the big ones past hecto or powers of 3. Well, powers of 3. So yeah, if you're missing any conversions, take a look at your formula sheet there. For the question 3 down there at the bottom, how many minutes are there in a year? How many days are there in a year? Technically, no. 365 and a quarter is the number of days. That's why we have leap year every 4 years. So use that 365.25 for that. And I'll see that last one. For 3B, I want you to give it to me in hours and in years. For 3B down there at the bottom, how long would it take you to count to 1 billion? I want you to give me that number in hours and years. Because it's way bigger than hours. I'm looking at that, so I don't forget that extra zero. That number is impressive. Hours and in years. Welcome to physics. The physics will start in a week or two. For those of you who don't like graphing, next couple days are gonna suck.